Hi, we're Team 13 from summer 2019. I'm Carter Sullivan.
I'm Gautam Pramod Kumar.
I'm Carson Woodward, and we did a project called Automate the Construction Site.
So what is your part of the project?
Oh, for my part of the project, I did the weigh station that the dump rover drives over.
Oh, how does the weigh station work?
Okay, well, the weigh station uses the combination of a load cell and actually a Wheatstone amplifier.
A load cell? What is that?
Well, the load cell is something that detects the weight of an object by the strain on the metal. We used a bar strain gauge load cell, and this just detects differences in resistance on the top and bottom in order to tell the weight of the object on top.
And how much can it weigh?
It can weigh about 5 kilograms, but that's way greater than we actually need, so the accuracy is a little low.
So you said it uses a Wheatstone amplifier. What does that do?
That's actually used, it's a reference resistor that you use to set the output voltages that come from the cell. That way you can check on the board for those values, send them into a lookup table, and they'll return the object's weight in grams.
So how does all this fit into the whole project?
Okay, well, the weigh station is actually located here. And the dump rover drives to the weigh station after it receives a load from the arm. That way we can load the dump rover, weigh the dump rover with its load, and then send that information to the server. All right, so what part of the project did you work on?
Okay, so I worked on the rover motor controls on this project because that's what makes our different parts move in the project.
Okay, well, how do you control the movements of the rotor?
Okay, so basically the rover here is working with two DC motors, and the motor feedback is being fed into the output controls on the motor shield. And basically I'm using that to read in how far it has gone, and accordingly I control the movements.
Okay, that sounds awesome. So how does that fit into the entire project?
Okay, so in our original implementation, we had a PixieCam on the arm rover, which would detect the blocks and tell the motor code to do like, hey, turn to the right by 5 degrees and move forward 20 centimeters or something. But we ran into some hiccups on that. So the way we got around that is we changed the implementation so that the Pixie would just be able to detect the block being there. So it wouldn't actually tell it the distance that we had to hard code in. So it became really important that the feedback and the logic for that was working correctly. So essentially, the feedback is being fed into external interrupts, which counts up the ticks. And when it hits a certain number of ticks, it knows it's moved a certain distance. So it's like 22 ticks is about a centimeter, and that's how I'm controlling the distance it moves. So when it gets a signal to move forward, the arm rover will move towards the block, and then when it's done performing its action, it will move back. So that's just the arm rover. For the dump rover, which is what we have here, when it's loaded, it has to move a certain distance to the weigh station. Then it has to follow a path which involves a straight line, a left turn, and another straight line to get to the dump zone, where it'll dump its load. And then it'll return to the load zone. That's basically the rover part of the project.
Sounds great, thank you. All right, so what part of the project did you work on?
So on my part of the project, I did both the ARM controls and the server setup.
Oh yeah, so tell me about that server.
So the server for us, in simple terms, is a way to connect to our database. Our database is important in that it holds the values for the state for our whole project, which determines all the different functionalities of our project. It also holds values for our weight and the color blocks that we're picking up.
Okay, all right, now tell me a little bit more about that arm. How does that work?
So the arm is pretty cool here. You can see it's a 3 servo arm. The servo on the bottom we actually don't use, although we could use to move the position of the arm. This middle servo controls the up and down movement of the arm, and this top one controls the claw opening and closing, i.e. the grabbing function. These servos, how they work, are by an output compare module on the PIC boards that we're using. The output compare creates what's called a pulse width modulation value. That pulse width modulation value sets a position for the arm, an angle of the servo motor. Now that angle determines the position of the arm, basically moving the arm throughout its functions and opening and closing the claws. Now we can set to different movements. We use those movements to determine throughout the project when we're going through to pick up the block, and it goes through to pick up, does a certain movement, and then when it goes to drop in the bed of the dump truck, it does movement as well.
Sounds great. Thank you.
I'm Riley Matthew, and my part of the project was working on the PixieCam. So originally, what we were planning on doing is having the PixieCam on the arm rover, and what it was going to do is it was going to kind of look for a block, and once it found the color block that I was looking for, it was going to let the server know that, hey, it's found the block, and then the rover would go and pick up that block. So originally, when I implemented it, I first taught the PixieCam what blocks and what colors to see through using Piximon, the software. And then afterwards, I had a state machine that went through and kind of figured out what part of the object block we were looking at for the information the PixieCam sends. Because for each object that it detects, the PixieCam constantly sends an object block. And for the information the object block is, it sends first 2 sync bytes, 0x55 and then 0xAA. It then sends 2 bytes that are checksum. Then it's 2 bytes that read the signature that match whatever the signature of the block that it recognizes. After that, it has 2 bytes that are the X center, 2 bytes that are the Y center, 2 bytes for the width, and 2 bytes for the height. And then this is like the order it's always sending in. So I use this to create the state machine that kind of figures out like what part of the state it's in. And so what I did is I calculated the distance of the object using a formula. First, I calculated the focal width and using like a known distance and the known width and height of the object block. And then so basically what I did in the state machine was once I hit the second byte of the height, I would then calculate the distance using the bytes that I've already seen. And then once I had that averaged out, once I had like 5 distances, I would average out the distance and send that information to the rover. And all this worked perfectly fine once when the PixieCam was on its own. But once our plan was to integrate one of the rovers and the Pixie onto one microboard. And once we tried to do this, for some reason the integration would not work and we could not figure out what was causing the issue. We tried implementing little by little. So we ended up doing a new implementation for our final demonstration where we simplified it and the PixieCam was on a separate board, but all the PixieCam was doing that it was just constantly looking for, does it see the block? So basically if it sees the block, it's constantly sending a yes put essentially to the server saying yes, it sees the block, and if it doesn't see the block, then it's sending a no. And essentially what the rover was doing this time, where it would go and pick up the object, and it would keep the rover would keep trying to pick up the object until the PixieCam said like no, it doesn't see the object anymore.